Okay, we're going to cram as much as we can about circular motion into a really short video, so hopefully I can keep this pretty short anyway. Not promising anything. Guess I probably need a dry erase marker here. All right, this topic, since this is an introduction to rotation, sometimes it's a little bit difficult because we're so used to everything being in a straight line back and forth, or maybe just even at a right angle. But we don't have to deal too often with objects that are actually going in a circular format. Okay, so let's take a look at some of the introductory stuff here. And I know this is a lot of writing on a board, and if my handwriting's bad, then I apologize, but we'll try to negotiate through this. While we're rotating, and we're going to start off and keep everything in a perfect circle. Okay, we'll eliminate all of the elliptical motions and so on. And for the most part, and especially early, our problems are only going to maintain a constant uniform speed about a central axis. Okay, so we're always going to maintain the same radius, and our velocity vector will always be drawn at a tangent to the circle. So hence it's called tangential velocity. Okay, and that magnitude, even though the direction is constantly changing, that magnitude will stay constant. Okay, so as this object, if we have an object placed at radius r from the center of the circle, and as it's moving around that circle, it's going to maintain the same speed. That's what uniform speed means. Okay, so anytime you see constant uniform speed, understand the speed isn't changing, the tangential velocity is the same at each point. Okay, and we're not so much worried about a directional component for this. Okay, so call the uniform speed, tangential speed, or tangential velocity. Many times it's going to be symbolized with a V, with a T subscript. To be quite honest, that's not super important to put that there. But if we know, we should know by now that speed is just distance divided by time. Okay, so it should make sense that our equation for this object going around in a circle is going to still equate to distance divided by time. And the distance for one rotation or one revolution from the center of the axis is going to be equal to the total distance, which is the circumference of the circle. So we have 2 pi r over t. Now, one thing, and this is a minor thing, but notice I changed this and put an uppercase T here. And the uppercase T is used to indicate period, because we could have a time period to get from here through 1/4 of a rotation. Okay, but the uppercase T is going to always symbolize the time period for one revolution or one rotation about the axis. Okay, now, so we have our distance, we have our time. Now, we also have another equation, another way we can look at some of these problems. Instead of thinking in terms of time, because some things rotate really, really quickly, and we're not so much worried about the time for one rotation, but we're worried about the frequency of the revolution or the rotation. Okay? And frequency is just the inverse of time. So 1 over time, so for the period for one rotation is going to be in revolutions per second or rotations per second. So it should make sense then that 2 pi over t is going to be equal to 2 pi r times the frequency. Okay? I think that pretty well sums it up on just the basic speed calculation for anything going in circular motion. We'll deal with a couple of practice problems here in just a little bit on the right-hand side of the board, and we'll kind of go over this in more detail at that point. All right. Angular velocity, and this is going to be the start of the next unit when we start talking about rotational kinematics and dynamics. The angular velocity, and I'm going to go ahead and introduce this symbol now, even though we will not be doing any specific calculations with this, but it's exactly what it says. It's angular speed. So it's by what angle you go through over a certain time period. So if we can imagine, we have 2 objects here. So let's say I've got one object on the outside at this radius and then one object on the inside at this radius. Okay? If I send them both through the same angle, so if we come down here and we notice, we have object 1 at a smaller radius from the center than object 2. Well, we should know by now, if we put a bunch of people on a rope and we start spinning that rope around in circles, okay, the person that's on the farthest end of the rope, the farthest away from the center, is going to have to move the fastest to get through and make one complete circle in comparison to someone in the middle, near the middle. they're not going to be moving super fast. Okay, so to compare here, angular speed is symbolized with the Greek letter omega. So it looks kind of like a funky W. So a lot of times in class, I'll even say W just to keep it short. Omega, and this is going to, it should make sense. This is going to be measured in radians per second. And those of you who know a little bit more about degrees and angles, one complete circle is equal to 2 pi radians. Okay, so hence tangential speed is 2 pi, so 1 complete circle in radians times r, which is the radius. So the further you get out, the faster you're going to be moving. Whereas angular speed, omega, when we get to this later, we can just drop the radius because the radius doesn't matter. Fact is, if we have these two people attached to this rope and we move them through the same angle, the angular speed is the same for both. You know, maybe they both go through 30 degrees or half a pi radian or something. Okay, but the fact is that the angular speed is going to be the same, but the tangential speed for object 2 is going to be greater than object 1 because he's further out on the arc. Okay, so hopefully that's fairly simple when we're discussing the concepts of just basic uniform circular motion. Okay. Now, let's change gears here for a little bit. Speed is constant at all points, as long as we're at that radius. Okay, any other radius measurement away, then the speed's going to be different. But the speed is constant. So if I measured the speed at this location, so we rotate him through, now I'm going to have my tangential vector drawn there. And then if I continue going around, you can see that the actual tangent to the circle is going to change. So even though we say that the speed is the same, the direction of the motion is changing. And if the direction of motion is changing, that indicates that there is acceleration. Okay? Now, the interesting thing about this, as this moves around the circle, notice the direction of the arrow change for the tangential velocity. It's always going to turn towards the center. Okay, so our acceleration vector is always going to point towards the center of the circle. Okay, so when we are moving at a constant uniform speed about a central axis, we're still accelerating, but we're accelerating towards the center, yet we're never getting closer to the center. We're maintaining perfect uniform circular motion. Okay, so the object accelerates to the center. And the equation for centripetal acceleration, that's where the little c comes from, centripetal acceleration is equal to the square of the tangential speed divided by the radius. Okay? So I know that's kind of hard to picture, that even though you're moving at a constant speed around a circle, but you just got to understand your direction is changing. Every second, your direction is changing. And the direction is always changing towards the center. Okay? Now, since acceleration exists towards the center of our circle, anytime we have an accelerating object, that means there must be a net unbalanced force that is pointing in the direction of the acceleration. Okay, and that goes all the way back to our linear problems in Unit 3 and any problem we've had since then. Okay, since we have acceleration and we have centripetal acceleration, that means we must have a net unbalanced force also pointing towards the center. So our force vector arrow is going to be pointing in the exact same direction as what our acceleration vector. Okay, so the centripetal force, remember, force equals ma. That goes back to Newton's second law. Well, the acceleration is centripetal, so if I sub that in, the centripetal force equation is equal to mv squared over r. So now anytime we have an unbalanced force that's generating anything moving in a circle, we're going to say we're generating centripetal force. Okay? Now, and that's one thing that this will drive you nuts a little bit too. Centripetal force is not a real force. We can't just have centripetal force acting on something. There has to be some type of unbalanced force that's creating the centripetal. Okay, so without getting into too much detail right now, if we can imagine this object right here is this far away and it's going in a circle. If I were to cut the string at any point in the object's motion, this object would just fly off in a straight line wherever that tangential velocity is pointing at that particular instant. Okay, so if I cut this rope right here, this object would just fly in a straight line. If I cut the rope right here, this object will fly that way in a straight line. Okay, and then it will just continue on at a constant velocity, whatever that tangential speed is, unless there's another outside force acting on it. Okay, so we have this net force that's making it curve. So that means the force is always pointing inside. But what's generating that force? Well, if you're attached to a rope, the net force is going to be the tensional force. Okay, and we have lots of examples of this that we'll explore in class later on down the road. Okay, if you're driving up over a hill, okay, at some point, your normal force up, as you go over that arc, that normal force pointing up is going to start getting less and less and less depending on how fast you're moving and what the radius of curvature is. When that normal force approaches zero, the only force acting on you is the downward force, and that would be your weight. But if the normal force reaches zero, then you would become airborne once you leave that hill. Same thing if you go down through an arc. So you're on a roller coaster and you go down a hill and you curve and go back up. It feels like you're being pushed down in your seat, but yet you're maintaining a circular motion. So you feel like you weigh more, and we should know by now the apparent weight in that scenario would be equal to your normal force. So now your normal force is greater than your weight going down, so you have an unbalanced force that's pointing towards the center of that circle as you're going through. Okay, so we can have friction that's keeping us on a rotating platform. That force has to be pointing to the middle. So some force, and later on we'll have to identify what those forces are and draw free body diagrams just like we did in Unit 3 in order to understand where the unbalanced force is that's going to be generating this centripetal force. And just like in Unit 3 when we were talking about linear forces, we'd write a net force equation, set it equal to ma. Well, our acceleration is just a little bit different now, because instead of being a linear acceleration, now we're dealing with a centripetal acceleration. Okay, so a lot of these problems would be very similar to what we've already explored. Let's take a pause here and I'm going to clear the board and let's work these 3 practice problems real quick. That way we got a little bit of an understanding of what we're going to be dealing with. All right, so let's look at the first practice problem here. We have an object that rotates at 250 rotations per minute, 0.3 meters from the center. And all we want to know is just how fast it's going to be moving. Okay, so we have 2 ways that we can solve for this. Since the 250 rotations per minute indicates frequency, we can just go ahead and solve this in one step. The other thing we can do is convert this to rotations per second and then inverse it and just solve for the time for one rotation. Okay, and obviously if it's rotating at 250 rotations per minute, that's going to be a pretty small time period per rotation. Okay, so let's just look at it and solve for it straight out with this equation. All right, so 2 pi times our radius, which is 0.3 meters, okay, times my frequency, which is 250 rotations per minute. Now, we need this to be in rotations per second, so I'm going to go ahead and convert and say that there's 1 minute and 60 seconds. Okay, so 2 times pi times 0.3 times 250 rotations per minute divided by 60 seconds. And this is going to give me 7.85 meters per second. Okay, we'll come back later on, and I'm sure initially you're going to sit there and wonder, well, how did we get meters per second out of all of this? Well, the rotations goes away. Okay, and we'll talk about how, there's 2 pi radians in one rotation. So we'll talk about how those units just kind of disappear later on. But we're still solving for speed. So this is the speed of that object at any point in that circle, as long as it's maintaining constant uniform speed. Okay. The other way to do this is we could use this equation, say t equals 1 over frequency, And we can go ahead and solve for the time period if we wanted to for one revolution. Okay, so we've got 1 over 250 rotations per minute. Okay, and that's going to give me minutes per rotation. So now we're going to, if we want to do this, we need to multiply it by 60 seconds. And that's going to give me 0.24 seconds per rotation. Okay, so now I can come right back up here and I can go 2 pi r, so 2 pi times 0.3 divided by 0.24, and I'm going to get the exact same answer that I got before. So it really depends on which way you want to look at it. If you want to stick with revolutions per second or revolutions per minute, you can use that. Just make sure we're in frequency. Okay, next problem. An object rotates every 0.5 seconds at a radius 2.0 meters. Calculate the centripetal acceleration. Okay, so centripetal acceleration equals v squared over r. Now, we don't know the actual velocity, and we could go ahead and solve for it and then sub it into the equation, but I like to go ahead and solve for everything at once. So let's go ahead and just derive out the equation. Okay, once again, we could say that v equals 2 pi r over t and just solve for this, but if I drop that in, this is squared over r. Okay, this is going to equal 4 pi squared r squared over t squared, and this is going to be over r. Now, this is the same thing as saying r over 1, so when I inverse this, I can say that this is 1 over r. Okay, and r squared cancels that out. Okay, so I'm essentially left with 4 pi squared times r over t squared when I solve for this. Okay, so if we fill this in, 4 times pi squared times my radius, which is 2 meters, and hopefully we can square 2 by now, divided by 0.5 seconds for one rotation. We got to square that. And that's going to give me a centripetal acceleration of 316 meters per second squared. Okay, so it sounds like a pretty big number there, but we'll start to make sense of some of these numbers later on. Okay, right now they're just numbers on the board, and when we start seeing them in action, you'll be able to understand a little bit of what we're getting. Okay, one more quick practice problem here, and then I will conclude this video. I know it's getting kind of lengthy, but I've covered a lot of material in a few minutes here. All right, we got 150 gram mass attached to a string moving in a circle with a radius of 0.8 meters at a speed of 20 meters per second, and I want to calculate the centripetal force. Okay, so force centripetal equals LMA, which is LMV squared over R. Okay, now, since we're calculating force, by now we should understand that force is going to be measured in newtons, and a newton is a kilogram meter per second squared, so we need to say that this is 0.150 kilograms. Okay, I gave you the tangential speed, so we're moving at 20 meters per second, which is pretty quick, because when I square that, it's going to give me 400, okay, divided by my radius, which is 0.800 meters. Okay, so that's a pretty simple problem. I gave all the numbers that were there. We didn't have to sub in anything, so that makes it pretty easy. So if I multiply those out, divided by 0.8, I'm going to get 75 newtons of force. And I don't necessarily worry about a directional component on those right now. It's always towards the center. So anytime you see the term centripetal force, we know the direction. It just depends on where our initial positions were if we wanted to actually have to indicate an actual direction based on where we started at. Okay, that's going to conclude this one. Hopefully you got enough information out of this to get you started on your way on centripetal motion and making sense of it.